Hello everyone. Welcome to the Link Tech Talks. My name is Colin Chandler, and our co-host is Mi Dai. We are both Link Frameworks project scientists, and I'm at DiRAC Institute, University of Washington here, and Mi is at University of Pittsburg. These Tech Talks include presentations and demonstrations showcasing work done by the broader Rubin software and archives community with the goal of further enabling LSST science. Now, unlike traditional talks you might hear at a conference, Tech Talks highlight technical aspects of work being done, including challenges that people experience. So we hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LSST data. Link Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. And so today we have two talks. They're each a little bit shorter than our usual 40-minute talks, and they're both related to the last batch of LINCC Frameworks Incubators. The incubator program this is designed to engage the scientific community in creating software tools for analyzing Rubin LSST data. And the current iteration is after these two that we're hearing about today, as especially supporting research teams to expand on early stage LINCC frameworks tools that are being developed. So two talks today are DeepDISC PhotoZ, integrating image-based PhotoZ estimation in RAIL, and lsdb-macauff, the trials and tribulations of catalog cross-matching in the era of LSST. Each talk is going to be about 20 minutes, and we'll have time for a few questions at the end or in the middle at the speaker's discretion. Please ask questions here in Zoom or in the Link Tech Talks channel on Slack. You can type the questions here in chat as well, or if you wish to speak, you can raise your hand at that time. And as a friendly reminder, these talks are being recorded and they will be posted on our YouTube channel. So first up is Grant Maris. He's a third-year graduate student at the University of Illinois Urbana-Champaign, researching AI solutions in survey science problems, including deep blending and photometric redshift estimation. So thanks for joining us, Grant, and go ahead and feel free to share your screen and take it away.
All right, thanks everybody. Thanks for the opportunity to talk to you guys today. So I'll be talking about the LINCC Frameworks Incubator that I did called DeepDISC PhotoZ with the support of everybody listed here and the whole LINCC team, LINCC Frameworks team. So thanks to everybody for all the hard work and support. So I'm not going to spend, I think, too much time on some of the photometric redshift stuff. Just I think that many of us are familiar with just the fact that we'll need redshifts for just a ton of different science areas within LSST, from cosmology to transients and more. And since we don't have spectroscopic capabilities with Rubin, we're going to have to use the available data, which is the photometry. So this color space, it's sort of this reduced dimensionality space, taking the entire SED, and then basically the colors and magnitudes that we get are just that SED integrated over the filter transmission. And so this is not perfect. The photometry is not necessarily perfect in estimating a redshift. There are degeneracies in this color space. Features in the SEDs can cause distortions in sort of in the color space. And so it can be kind of a challenge to basically get a redshift just from this sort of reduced dimensionality space. And so many different PhotoZ algorithms have been developed, and I've listed them here kind of in three different categories. Template-based codes, things like BPZ and Lefebvre, and these are codes that basically use a forward model and a set of STDs over a redshift space, and then find some best fit redshift based off of the input photometry. There's also machine learning based codes. These are codes that basically take in the photometry and then some sort of ground truth redshift, and learn sort of a nonlinear mapping in between that photometry space and the output redshift. And popular codes are things like FlexiBoost and TPZ. And then I've also included here a separate category that I think merits its own category, is image-based codes. So previously in the codes that I mentioned just now, those rely on sort of catalog information. So just sort of this tabular data of fluxes and magnitude errors in different bands. However, there is sort of this growing area of research and application of image-based codes that basically just use the pixel level information, taking an image of an object, running it through some sort of deep learning algorithm to get an output redshift for the given object. And so these can also be, rather than a point estimate, we can also get a full sort of probability distribution of a given redshift. And this is really useful in terms of basically characterizing uncertainties, the fact that there are those degeneracies in the color space, and basically just propagating uncertainties through for just sort of fully Bayesian analyses. And so codes are basically, many codes are designed to basically spit out a PDF of a redshift, not just a single point estimate. And so we can kind of judge the quality of an ensemble of like predicted PDFs based off of metrics and sort of qualitative figures. So like in the top right there, that's a pit histogram. It's a common sort of visual diagnostic of an ensemble of PDFs. Ideally, it's a uniform distribution. And then if your PDFs from your PhotoZ estimator are too narrow or too broad, you can get these kind of convex or concave features in the pit histogram. And then also traditional measures of how well a PhotoZ code works, things like the scatter, the bias, and the outlier fraction. And these are taken from basically reducing that PDF down to a point estimate, so commonly like the mode or the mean of the PDF, and then comparing it to some sort of ground truth or true value of a redshift. These are just common sort of methods of diagnosing the accuracy of a PhotoZ code. And so in order to sort of unify a lot of different PhotoZ codes and just have a sort of umbrella framework for housing, training, and estimation, and just containing all of these codes, LSST DESC developed this code, this package, Redshift Assessment Infrastructure Layers, or RAIL, which basically houses all of these, these previous codes that I mentioned, and many more, and also sort of has this common framework for testing all of them. And so the goal of this incubator was to basically add DeepDISC, which is this image-based estimator we're developing, into this RAIL framework. And just a quick background of DeepDISC. This is a deep learning model. So DeepDISC stands for Detection, Instance Segmentation, and Classification with Deep Learning. And basically, it's capable of, given an image of astronomical objects, identifying them with some sort of bounding box, indicating where it identifies an object, producing a segmentation mask for each object, and then also doing some sort of downstream task, like object classification, or for the purposes of this incubator, PhotoZ estimation. And so last year, we released a paper applying this framework to real images from the HSC deep and ultra deep fields, and performed this detection, deblending, and then star galaxy classification for that work. I won't get too into sort of, I think, the nitty gritty of DeepDISC, but suffice to say it's built off of this Detectron 2 repository, which houses a lot of like state-of-the-art computer vision models. And so we can apply things like CNNs, but also sort of more, again, state-of-the-art things like vision transformers, and just newer and improved models to try to sort of boost our capabilities. So for DeepDISC PhotoZ, basically we're just taking our sort of baseline DeepDISC network, which does those tasks that I mentioned before, and then adding on sort of a module that encompasses a mixture density network, or just basically a parameterized a Gaussian mixture model, which will output a Redshift PDF for each identified object that's just parameterized by this mixture model. And so a lot of the sort of challenges of this incubator were just kind of meshing these two packages, DeepDISC and RAIL. I listed a couple points here about each sort of each framework that I think made it a little bit tricky to combine these. And I might not have time to go into a lot of detail, but I do want to just stress that like this was a lot of work went into thinking about how to sort of combine these packages and to produce something that was streamlined and worked well. So this was a lot of effort went into these areas. So just a couple of points about meshing these two packages. RAIL is specifically designed for tabular inputs, so catalog level data. As I mentioned, DeepDISC uses images. And then also, because DeepDISC is a supervised method, we also need those locations, segmentation maps, redshifts, anything that it will then predict it needs to be able to train on. And so the data structure for that was a little bit tricky to try to basically mesh with the RAIL existing sort of file IO structures. And just through some clever sort of encoding of these of this metadata into JSON strings and just applying this sort of encoding to the existing RAIL framework, we were able to basically get it working without sort of inventing a new RAIL data class or anything like that. So we're able to use the existing RAIL structure using some clever sort of encoding of metadata and then flattening the images to basically sort of mimic tabular data. Another thing is that since RAIL is built off of the LINCC framework, which is basically as a pipeline software, LINCC sort of wants a single input file to sort of track through a pipeline of training and then testing. This doesn't really work well with DeepDISC just because it can't handle sort of a massive amount of images at once in memory. And so we implemented this caching structure to basically contain everything in one input file at the start of a pipeline, cache the images to the disk, and then have DeepDISC read from that cache directory using its normal sort of PyTorch-based data loading capabilities. This will actually be useful for other codes in the future that use these sort of PyTorch-based data loading backends. And then as well, it's just useful for codes that maybe need to sample from different portions of the data, differently sized portions of the data at different times for codes that maybe incorporate clustering information and things like that. So I think this was kind of a useful lesson learned from meshing these two packages. And then also, we now have implemented a basically fully parallelized version of RAIL DeepDISC such that it utilizes the parallel file IO capabilities of RAIL. And so now we can run testing across training and testing across multiple GPUs, across multiple nodes. So fully parallelized. And then also we've cleaned up the sort of base DeepDISC repository. A lot of work went into sort of streamlining that. We have documentation, improved just API across the board, implemented the Python project template. And so I think we've really put together some sort of nice and approachable repositories for future use. So then to present a few results of just sort of benchmarking DeepDISC with some other methods within RAIL, what we did is took images from DESC DC2 and then the truth catalogs for redshifts, and basically took a set of 1,000 images that are sort of a cut from a patch. A patch is a unit of an image within the DC2 sort of framework. And basically each subpatch image that we sampled had a couple hundred objects. So overall, we're training on something like a couple 100,000 objects. After training, we then produce basically object locations, again, footprints and Redshift PDF for every object. So then afterwards, we match to the object catalogs within DC2 to basically compare to some of those more traditional catalog-based methods. So there's an example of sort of the training and the inference after DeepDISC has been trained. So some preliminary results, yeah, basically comparing BPZ, which is one of those template-based methods that I mentioned earlier, to DeepDISC. This is on a test set of something close to like 1 million objects. And so you can compare the pit histograms and the QQ plot, which is that red line that you lie along the diagonal, versus a pit histogram, and then as well as the sort of scatter plots of the point estimates. And so we can see that DeepDISC is in general, it doesn't have these sort of spikes that BPZ has at these low and high pit values, indicating that for BPZ, some of the PDFs might be too narrow. DeepDISC gets a more uniform distribution. And then as well, the bias, the scatter in the bias, and then the outlier fraction defined by some cut in the scatter are all lower for our DeepDISC runs than for BPZ. And then here comparing to another catalog-based code like ZBoost, again, kind of has these sort of peaky aspects of the pit histogram at low and high values, which we don't see within our DeepDISC run. You may notice that so not a lot of objects are detected, or not detected, excuse me, not a lot of objects have a predicted redshift above 2.5. I think this is largely due to just the N of Z of the training sample. So we're looking into some data augmentation strategies to basically allow the networks to learn more from that sort of less information at high Z. Some comparisons of just the PDFs of a couple of unique objects, just to get a sense of how the PDFs from different codes might look. And then there's a N of Z histogram on the right that's derived from the mode of each PDF. You might notice there's a lot of peakiness in the FCB histogram as well as BPZ that you don't necessarily get with DeepDISC. It's a more of a smooth distribution, which is more what we would expect. And then lastly, just some plots showing bias. These are point metric estimates as a function of true Z on the left, and then reddening on the right, which is I would think it's the reddening plot is interesting in that DeepDISC is showing basically not a strong bias with regards to galactic extinction. Which is good in that we didn't actually include that information in the training, and it's still sort of robust to it. So it's implying that this method may be more robust to other observational systematics as well. Yeah, so just kind of to wrap up that, to summarize, we're basically validating DeepDISC by comparing to some catalog-based methods on DC2 data. We see that it's comparable or better than catalog-based methods and basically the PDFs and the point metric estimates. Potentially, performance may be affected by some observational systematics and underlying effects in the DC2 data. And we plan to further test the effects of blending, so recognized and unrecognized blends, using a simulation framework that we also developed as part of the incubator that basically includes the Cosmo DC2 catalogs into the blending toolkit. So the blending toolkit is a framework based off of GalSim that will simulate images, and you're basically able to control the level of blending. And so by adding Cosmo DC2 catalogs, we can also incorporate, with these bulge and disk model images, we can also incorporate chromatic effects that weren't previously present in some blending toolkit and other blending toolkit catalogs. And so we plan to basically produce sets of these blends and test the effects of basically how much blending, whether it be recognized or unrecognized, affects photo-Z estimation of both DeepDISC and then traditional catalog-based methods. So we have the repositories up, documentation, and a paper draft going. So just wanted to wrap up by saying huge thanks to Drew, Olivia, Doug, TQ, Jeremy, Melissa, Alex, just everybody that helped this effort. Thank you for all the hard work and support. And at this point, happy to take questions.
Awesome. Thank you very much, Grant. I will actually use my speaker's privilege and ask the first question, if that's all right.
Of course.
You mentioned, obviously, you're working with image data. I think you said something on the order of thousands for these subpatches, et cetera, like what are you anticipating you're going to need? Like what size are these cutouts sort of in pixel space roughly? How many of them do you think you're going to need with LSST? Are you going to use the image cutout service with this, or use the full images? And what do you need to do that in terms of computing resources, et cetera?
Yeah, it's a good question. Yeah, it kind of does depend a lot on the computing resources. So one of the nice features of these models is that they can actually work on variable image sizes. So for these results, I trained on something like 500 by 500 pixel images, and then the test results were ran on 1000 by 1000 pixel images. And really that can just get pushed up to as much as you can fit into memory on a GPU. And so it's kind of limited. Basically, that's the only limitation in that aspect. So likely, just depending on sort of the memory of the available GPUs, you could potentially run on an entire patch at once. But if it turns out that there's not enough sort of memory capability, then yeah, we would have to basically do some sort of cutout service and just take some cutout of that. But once trained, we only need the image. So that's straightforward.
Cool. And just how about a ballpark? Like, do you have any sense of how many times you're going to be doing this daily? Like,
that's a good question.
I'm bad at guessing these for things outside of solar system.
That's a good question. So yeah, for our tests on, let's say on the test set, we had again it was closer to 2000 images that were like 1000 by 1000. So that's the equivalent of something like, I don't know, call it 100 patches roughly. So it took about on a single GPU, it takes something like an hour for that. So it's also very parallelized. So yeah, I guess to give you some more concrete numbers, about an hour on a single GPU for about 100 patches. And then it's fully parallelized beyond that. So could be ran on multiple nodes.
Awesome. Thank you. We have time for one or two more quick questions. Well, we can reserve that time for the end of the talk, unless I'm missing anybody here. So yeah, thanks again, Grant. And let's ask.
You muted yourself somewhere in there, but I assume you meant that we should switch ends at the half.
I'm sorry, run that by again.
Oh, just I should. You had muted yourself, but I was assuming you meant I should take over.
Yeah, go ahead and start screen sharing. Yeah, I just wanted to double check there, looking at my stats. So Tom received his PhD in 2018 from University of Exeter. He spent 2 years at Space Telescope Science Institute developing AstroPi code, and since 2020 has been working in the LSST UK consortium on the problem of catalog cross-matching for LSST, which is quite pertinent for today. So with that, take it away, Tom.
Okay, hopefully you can see my slides, you can hear me, you can see me, everything should hopefully be working.
Looks good.
Lovely. Okay, thanks everybody for coming today to hear about me complain about something that I suspect is not something most people think about as much as I do. I might be the person in the world who's thought the most about the problem of catalog cross-matching in total, which leads me to this talk today with my motley crew of my LINCC framework buddies here, who essentially have helped me try to solve this problem for you so you don't have to. But before I get into the incubator itself, just a bit of background on catalog cross-matching, because as I suspect quite a lot of you maybe haven't really used it. You just use data sets that are provided for you, or if you do catalog cross-matching, you've probably heard of nearest neighbor matching, where what we want to do is determine whether our two objects detected, our black circle here and our red circle over here, Are they one real astrophysical object for which we can combine all of our magnitudes and get a spectral energy distribution, or are they two real stars for which we therefore have flux upper limits in the respective catalogs, and therefore we have a different spectral energy distribution from two different sources? And nearest neighbor matching basically boils down to you take your object and you look for the nearest object on the sky in the other catalog, and you say, that's my guy. And it essentially boils down to constellation mapping. We have our pictures, we overlay them, and what we're looking for are those objects. You can see those three bright objects in these pictures here. Are they the same object? Well, probably. But how do we do that mathematically? And that was fine for most of the history of photometric catalogs. Nearest neighbor matching, or sometimes taking the brightest object within some critical cutoff radius, was pretty good, worked fine, until the Vera C. Rubin Observatory's legacy survey of space and time basically just has hit the wall of this no longer working, where inside our critical cutoff radius, perhaps 2 arc seconds is a typical radius that people use for nearest neighbor matching. In LSST, there will be at least one randomly placed object in addition to the true source in every single 2 arc second circle you put down anywhere in the galactic plane in single visit images, and there will be something like 10, maybe 7 in every single bit of the galactic plane in the bulge, in every circle you place down. 7 extra sources competing for that nearest neighbor match. And at random, one of them will pop up here, slightly too close, and you'll be dragged away from the true match, and it'll be something like 2 or 3 of these in these circles in the extragalactic sky. Better, but still, you'll be spending a lot of your time just dealing with all of these false positives, these incorrect matches with this algorithm. So my slightly dramatic statement that I put at the bottom of the slide here is that nearest neighbor matching will not work in the era of Rubin. But luckily, that's not the only algorithm that we have that we can use. So we can turn to probabilistic cross-matching, and skipping over a whole lot of development over 30, 40 years of history at this point, we can skip to, using my own paper as the example, some complicated equation, but the point is it allows us to introduce 3 new things. The first is we don't have to consider sources in isolation anymore. We can now add the extra sources in our orange circle catalog, and then we can start to resolve all of these things simultaneously, building positive reinforcement from these 2 objects match and these 2 objects match over here. We can use the brightnesses of our objects to figure out what sources are matched to each other, as well as just using their positions, and we can consider the precision with which we think we know where these objects are on the sky. So in my slides, I use rainbow circles here for my precision, so this object is much more precisely known on the sky than, say, this one in the background, which is far noisier, has a far more uncertain observation. So to reject these false positives, as I said, we can include the photometry of these objects, which basically boils down to, on large patches of the sky as an ensemble, the correlation between objects that lie on top of each other in our images, as I showed you before, reinforce one another. So if I take all of my Gaia 15th magnitude objects and I look near them on the sky, so I take my 2 Gaia objects here, and then I look just near them around them, they should have, in my example here, an IFAS I-band object, a 15th magnitude object, because the G-band and the I-band are roughly the same, so they should have the same brightness. So therefore, in my example, I've got these 3 competing false matches with different brightnesses. And then here, I've also got different false matches, but I've also got my 15th magnitude source. You notice that these red false matches have much different, broader ranges of brightnesses than my correlation, my true counterpart, building me a nice tight distribution of counterparts and a much broader distribution of false matches. There's a slight subtlety here in that what we would naively want to do is take a little circle around our counterparts and say, okay, that's my real object and it's some fake sources. What if I draw another circle over here, which should only contain fake objects, and subtract it, getting counterparts plus field minus field equals counterpart. But you can't quite do that because of a known problem where we over subtract our objects if we take our black circle and we try to subtract it from the red circle. So we have to do a little trick to overcome that, but otherwise we can solve the false positive problem. Back to the astrometry, which is where the rest of this talk will largely lie. That the rest of the point of this incubator lies is in these rainbow circles, where what we want to think of these as being the probability of the true position of this object being somewhere in these contours, given where we measured the object to be. And the key takeaway is that this astrometric uncertainty function, which I independently named in my first paper during my PhD, before discovering that Gauss originally referred to the Gaussian function as the astronomy error function, which I thought was just a nice historical happenstance, that they can be more flexible than this. But throughout all of the literature, as far as I'm aware to date, they're not. They're all assumed to be Gaussian, these rainbow circles. But what can we do if we extend that? We relax this assumption of Gaussianity of the astrometric uncertainty function. So in this example, what I have is Gaia-wise matches as our test bed, but really you can think of this as being a Euclid-Rubin match, where we have some very precise data. Gaia has exquisite precisions, as I assume most people should be aware of. If you've used Gaia data, you know how good they are. We can think of the Gaia observations as our truth, our ground truth of where our wise objects should be. And if we painstakingly create a bunch of separations between our Gaia and our wise objects, removing any possible contaminations, we get a very pure sample, two different samples in red and black here. We get two different distributions of separation, of deviation of the wise object from its true position. But the thing is that with the quoted uncertainty of these wise objects, these separations should follow this black dashed line. And I hope you can tell that they don't. So the point is, what have I done to make my black and red solid lines go through my data instead of the black dashed line? Well, if you remember, I originally showed you this image of the wise, a picture of a wise observation in the first place. And the first thing you see in this is it has noise. You can see sort of salt and pepper background. There's noise in the background. There's noise in the image based on photon counts, which is what causes the centroid precision, this original Gaussian uncertainty that we see in the first place. But also, these objects are two-dimensional on the sky because of the telescope optics, blurring out our point sources, hence our point spread function, which we refer to the PSF as. And what this does is block out the light from sources for the fainter objects behind it, which we saw was true for the photometry. But also, this affects the astrometry because these objects don't go anywhere. They get absorbed into these central objects. And therefore, we have an additional deviation away from true position caused by the perturbation from these blended unresolved contaminants. And we can then model this. So what we have to do is we have to build a model for our universe, and then we throw darts at a dartboard, essentially doing what the DeepDISC thing did with the Cosmo DC2 idea of blending, but we do it sort of just at a catalog level, where we build simulations, realizations of our density of our objects as a function of brightness. We then put down a little circle for a PSF, and we say, okay, well, what if there's a contaminant that's slightly fainter than our object? Maybe there's two more that are a bit fainter than that. What would the perturbation of these three contaminant objects be on the central object inside this PSF? And then we do this a whole bunch of times, and we get a distribution of these perturbations, which then, for Rubin, you get something that looks like this, where my rows are single visit 24th magnitude and coad 26th magnitude Rubin observations, and then I've got the galactic center on the left and somewhere just outside of the galactic center on the right. And then you can just see that depending on where you want to observe in the sky, this effect is very significant. Obviously, the further you go away from the galactic center, the less crowded you are, and the brighter you are, the less crowded you are. So the more you come down to the bottom left here, you can see that the red line and the blue line there just don't agree. So therefore, if you didn't take this effect into account, you would believe that two objects were too far apart, well, one in each catalog, to be considered counterparts to one another, and you would then say they're two different objects, which would be incorrect because you just haven't taken into account this systematic. But you also have to account for this outside of the galactic plane, where, say, you have a supernova that's gone off, and you want to find the progenitor of this object in your very deep Rubin observations. The progenitor being very bright would not be very affected by perturbation from these much fainter objects because it's become 10 magnitudes brighter or something. But the progenitor would be buffeted around in this sort of very noisy, very crowded sky that you're trying to find its original, the star that's exploded in. And you might lose something like 5% of your progenitors if you didn't take this effect into account with some critical cutoff ranges. But also, because this is a symmetric effect, if you're looking for these things in the infrared, then you have to take into account the effect of crowding in your other catalog. And Wise and Herschel, at least, especially, are very, they suffer very much from crowding at the same level that Rubin will do. I'm running a little bit short on this bit of the talk, so I perhaps will skip over this, largely leaving this slide in for posterity, for anyone who wants to go back to look at. But there are extra pieces of information that we can get from these probabilistic matches, such as, I just want to highlight, the one point is that we can subtract the brightening of these objects. As the other hidden unresolved contaminants get absorbed into our now composite object, they not only change where the position of the object is, they change the photometry, they change the flux and the magnitude that we measure. So that's one thing that then we can help to subtract back out with our modeling these observations. And then I'll just pause here. In the first half of this talk is a very compressed sales pitch on cross-matching and then sort of why you should care, to see if there are any questions specifically on the background before I plunge on to LINCC Incubator material.
I see, Nevin, you've got your hand up. Go ahead.
I was wondering, Tom, if you can do, and I think you wrote a sentence here, or you could use this movement, right, to detect variability, right? If you think that something has moved on the sky, that might be variability. Can you just, spend a little bit of time? Is like that's something that is kind of planned for LSST? How does that actually work, and etc.?
Yes, any data set that you have time series. So, for example, there's the VVV survey. Essentially, because we match something both in position and in brightness as two they're separable pieces of information. You can just multiply the two probabilities together, essentially. You can use this figure on the left here, where you consider the object both photometrically, the odds ratio of match versus non-match just in brightness, and then just in position. Then there's sort of this interesting phase space appears where the objects that are both good astrometrically and photometrically are good matches. If you didn't include, say, the blending, you'd end up over in this red box here where your model is just misspecified. But the variability is this orange box in the bottom right, whereas you match the objects through time. So if you took every epoch observation of the same object, or what you thought was the same object, matched through time, you would essentially see this object move up and down in probability of photometry. But because it shouldn't move too much because the crowding should be reasonably static, if you've got the crowding model right, it should just sort of go up and down. And then
how does this, if you have real variable objects like AGNs and such, is that like a noise to your model, kind of? There are a lot of real variable objects.
Yes, so you'd have to know which, I guess, yeah. So I don't know how you separate the two, just based on the figure, but you could model both of the effects. But yes, as an object moves across the sky, it sort of, it runs over a contaminant and that brightens it slightly, and then it perhaps moves away and then decreases again. That would perhaps be scatter in the astrometric. So real variability should just go up and down. But perhaps as objects are buffeted around, they'll sort of move slightly more erratically in a diagonal. So that might be one way to do this.
Thank you.
Great, thanks. That answers my moving object question. So I think we can continue on in the interest of time.
Yeah, so just, I think I forgot to highlight, just to here somewhere. Yes, so obviously I mentioned the most important component of the astrometric uncertainty function, but you can include any other systematic. So if for objects below the single visit limit in Rubin, you won't be able to get proper motions. So we have a model to include unknown proper motion of faint but still slightly moving across the sky objects. But yeah, that will introduce another drift separation between, say, Rubin objects, and if you needed to go back to 2 mass, you've got 30-year baseline. You can include any other kind of movement on the sky that you think might happen in this same framework. But if I hastily skip forward, yes. So that was a whole lot of theory, a lot of work that had been done previously. But unfortunately for us, the problem gets worse because all of that complicated cross-matching is tricky now. That's not actually the most fundamental problem we have with cross-matching anymore. It's the fact that there are going to be 30 billion objects, and therefore every single thing we thought of with catalogs has gone out the window, because you can't just download all of the data. You can't just run things on your laptop. You have to take your scripts to the data. You have to, suddenly every problem you have is basically an HPC problem, is a big data problem. So the LINCC people have been working on solving the cataloging part of this with LSDB, the large survey database, and then HipScat sort of built as the layer below that to solve the even more fundamental problems that we'll have with the Rubin data. So all of this very much under the hood. You have LSDB doing the science, and then you have HipScat, which is how you load your surveys. Underneath that, we have the fundamental of HealPix, which is this way to chop up spheres on the sky. Spheres in general, because of course we could turn inwards. I just found a nice picture on their website. You can use this to represent the Earth as well as the celestial sphere. But the idea is we start with equally spaced bits of the sky, and then we can chop those up into increasingly small squares, and then we can basically boil our problem down into nice small compartmentalized bits that then can be distributed. So what can we do with this? What have the LINCC people already done as part of this? So we can make our catalogs be HipScatted, as I believe is becoming a verb, where we take our original data. You have NeoWise as one of the examples on the website. You have a really big comma-separated variable file, and you break it down into this HealPix-based order format, so that you know which of these little squares is which, and how they know which ones are their neighbors and all of this. And once you've done that, you can do things like spatial analysis. This is the fundamentals of what we're actually doing, where you load some example data, and this is one of your little squares on the sky, or quite a big square because we're low order. You can then do things like cone searching, and then you can take cutouts of the intersection of one of your pixels and some search. And then on top of that, LSDB does the science. So say we're looking for a supernova between the ZTF data and NGC. We load all of our HipScat data. We filter for redshifts because we know our supernova is quite close. And then we match all of our observations, and we go, okay, well, we found the nearest one, and you can plot that, and you can say, okay, I found the supernova that went off in this particular galaxy. But the problem with that is the example is cross-matching ZTF with NGC, and the default algorithm is a nearest neighbor match. And somebody earlier in this talk, I can't remember who it was, very boldly stated that that was going to be a bit of a problem. Hence, lsdb-macauff. The best of both worlds, as I very dramatically have said here. The goal was quite simple: combine LSDB and Macauff. But that, turned out to be quite a lot of work, quite a lot of commits in there's like 5 different GitHub repositories, which broke down into, well, one of the things we actually had to do was I ended up taking 3 months of my time during this incubator to work on this as well. And largely my part of the project boiled down to changes to Macauff. which surprised me a little bit because we had said, we have this nice complete package and we'd like it to talk to your thing. And it turns out that some changes had to happen on our end, such as our work, we had used a different Rubin-based way to break up the sky, which worked on linear rectangles. You chop the sky into an exact grid that is 90 degrees to right ascension and declination, and we had based a few assumptions on that. But of course, HeelPix looks a little bit more complicated, and the shapes are slightly different. So therefore, we had to change our algorithms to be able to handle a slightly more generic shape of, well, this is your cutout, rather than it being just a rectangle. We also had basically baked into our code base the I/O and the actual algorithms, everything I just talked about in the first half of this talk in code form. They sort of talk to each other quite freely. They bounce things back and forth. But what we actually had to do was split those apart so that LSDB, with its particular requirements, was able to talk to the very internal bits of the code that actually it needed to talk to, and not worry about the fact that I'm loading a CSV file from this particular place on my computer. And again, LSDB, because it requires DESC, there's a few requirements on the LSDB side with parallelization, and some things had to be pre-calculated rather than calculated just during the workflow, which we had previously done. But also, I think the biggest surprise for me was the meta work, actually the running of the code base, because as I said, we thought we had quite a mature code base. You know, we weren't coming to the LINCC people going, I've got this science idea, please can we make a software package that can do it. But we found quite a few places where the code base could be better. Largely, the big one for me was the fact that we were using setup.py to compile our Python, as quite a few, almost all software packages of recent years have been doing. But that is, soon to be deprecated or has been deprecated. So we future-proof that so that, in year 5 of Rubin operations on perhaps at least on the in-kind contribution side of things on my other job, we weren't suddenly finding that, oh, this doesn't compile anymore because setup.py doesn't work. So that was good for us. And things like the Python project template we applied, which was quite an interesting challenge because actually some things we already had and there were some bits that could be added, such as I hadn't set up linting in a particularly robust manner. We weren't pip installable. They added version tags, all of these things. And I just hadn't got around to doing read the docs. As anyone who's set up a read the docs account might know, it's a little bit of a needle you thread to get it to work smoothly. So I appreciated the somebody sitting over my shoulder while I did that as well. But then on the HipsCat level, the level below LSDB, there were some changes that needed to be made because you had to be able to load our pre-computed association tables out of HipsCat so that they can have this order and directory parquet format. So there were some changes that were needed to be done there, and then now you can load our static sky association tables, and then you can just sort of view them within HipsCat. But also, once you've done that, then you can load them into LSDB, where LSDB then reads from HipsCat the files, and then the cross-match is as simple as this one line over here. You join Gaia to WISE through our association tables that we are running separately. We'll be doing yearly releases of LSST and a whole host of catalogs. And then you can also filter for things like match confidence, which you couldn't do with the nearest neighbor match. And then finally, we called this lsdb-macauff because there's this the middleware that talks to both LSDB and Macauff, so that if you're running LSDB on a small bit of sky, perhaps you've got a star formation region you care about, you could use the Macauff algorithm within that, and you don't have to rely on the built-in KD tree anymore if you don't want to. So that's lsdb-macauff. Again, I described it as the best of both worlds. Macauff is great, LSDB is as well, and now they can talk to each other. And I'll end there. Thank you.
Awesome, great. Thanks so much for that talk. Yes, that was fantastic. And we do have a couple minutes for questions. And I will swoop in there with with presenter privilege again and just ask, sort of following up on Nevin's earlier question, and because I'm a solar system person, so asking for a friend, but how do you handle the high proper motion objects, or is that, do you have any ideas?
So I guess I think the solar system is the weakest point. If you specifically want the solar system, we don't because we have to recreate the universe.
Or high proper motions. Let's stick with high proper motion stars. I don't need to bring
high proper motion in general. There's the two parts for the astrometry. If you want those objects, then all you care about is what the background looks like. And we simulate a generic sky. You know, you've got the galactic plane, and then you've got some galaxies, and you redshift those, you extinct those if you're in the galactic plane. But it's statistical. It's not a real data set. So the idea is, as in a probabilistic fashion, the universe might look like all of these different realizations. So then as the object moves, it will then have an uncertainty, a rainbow circle contour based on where it is in each of those places. So we can do that. We then build proper motions, or can build proper motions. I didn't have time to talk about this here, but we can build it based on a generic Milky Way galaxy. So I guess the point is, if you have a specific solar system object, we don't simulate that. So therefore, you won't have the high proper motion of a solar system object in your potential unknown proper motions if you don't know the proper motion of your object. But on the photometry side, we build our likelihoods from the data. So it's if you squint at it, it's a naive Bayes classifier. So if you have enough objects to be represented, then you're okay. The solar system objects are going to be relatively rare, so then you run into the training set sample size problems from machine learning a little bit. But the photometry is not orders of magnitude. It's a tweak on, if you've got two equally likely positions, it picks one. It's not going to, if your objects overlay each other, the photometry won't just say, no, definitely not, can't be matched. So I don't know which of those bits are most important, but this is for the static sky more than the moving and the weird.
Okay, that's a fair answer. I'll accept that. I'm used to this answer.
Yeah.
Nevin,
sorry, I was just gonna say, if you've got any ideas of, we can just keep adding models to our model. So if there are any quick and easy, because we have compute limitations, but if there are any nice, simple solar system models we could add, then we could think about extending. But I'd listen to Meg's talk from the Sorka incubator, and that seems like that's a whole thing in and of itself.
That's fair. Yeah. I guess, let's see. Okay, Nevin, you got your hand up. Go ahead.
Thankfully, I never heard of proper motion. So what I wanted to ask you is, let's say that it's kind of two questions. If I wanted to use that something which is not LSST, let's say I want to do Gaia and something comparable to Gaia, let's say ZTF, I have a question like, A, how difficult would that be for, let's say, myself? And B, what do you think is the fraction of sources that are misidentified with the nearest neighbor when you are not operating at LSST depth, when you're operating at, let's say, today's survey's depth, comparable to Gaia?
Gaia to a nice, well-behaved optical survey it'll be less than 10%.
I didn't say well-behaved. I said ZTF.
Okay. I don't know ZTF.
Sorry, that's just joke for myself.
Well-behaved it is.
Okay. Yeah.
So to mass, you're looking at maybe 5%. Pan stars. It's percent, because it depends on the number of objects in your catalog per point spread function area.
Yeah.
So WISE is a good example.
Worse PSF, the worse it gets, I presume, right?
Yeah, because WISE has the same number of objects in its PSF that Rubin will, is why it's our test case.
And can I get better result than nearest neighbor matching without running the full trilegal, or like kind of asking you, let's put it that way?
Yes, there are steps you can take. You don't have to go 0 to 100 to full full MacAuff. And one of the things that came from the incubator, as I say, there's loads of work. You can just keep extending your ideas to infinity. One of the things is we almost need a PSA campaign, a workflow to be like, if you have this problem, you probably want this, but you don't need this. If your problem gets worse, you need to do this, and it's a choose your own adventure type problem where adding in the uncertainties and resolving all of your objects simultaneously solves some problems. Adding the photometry solves some other problems. Adding the deviation from true object does something else. That I think is going to be needed as we ramp up, because LSST in the galactic plane we know needs all of these things. But yes, Gaia to SDSS doesn't need absolutely every trick in our toolkit right now, and some of them are computationally heavy, so not using them would be good. But it is but each individual pair of catalogs, you have to figure that out for yourself. This is the real problem with this. Is the downside. Is why I'm hoping that we can basically do all of the heavy lifting for the astronomer, so they don't have to.
That's a great answer. Thanks for that, Tom. Okay, one moment here. And so with that, let's just thank our speakers again, Grant and Tom, for their excellent presentations. And thanks to everyone for attending today's Tech Talk. And our next Tech Talk will be about the Think Broker, and will take place on April 11th at 2024 at 10 a.m. Pacific. Also, please join the link hashtag #LinkTechTalks, that's hyphenated, channel on Slack, and join the link LINCC at lists.lsst.org mailing list for more information and future announcements. So today's Tech Talks will be available on our YouTube channel within the next few days. And with that, thanks again, and everyone have a great day.